Okay. This is our class number 3, right? And yesterday I put the workshop number 3 on the website, so you could download and take a look. And if you had questions, we could discuss it during this class. Some of you might have seen, others might not. Okay. So I'm going to give the class, and you can ask questions if you want. So the objective of this class and of this workshop is to use a model function, which is a potential function, as an example for you guys to do structured programming. Structured programming, right? And also to use the tools that we have in MathCAD, surface plot, contour plot. Okay. And we are going to use this type of problem that is typical in electromagnetic theory to do these things. The potential function allows you to obtain several information from a system of charges and conductors. If you get the potential function, you can determine the electric fields, you can determine energy of a set of conductors or charges, you can determine capacitance of a structure and so forth. Okay? So potential function is very important, not only in static problems, but also in dynamic problems. They are always the intermediate function between the original problem and the final function you want to determine. Okay? So it's an intermediate step. In electrostatics, the potential function is this intermediate step. And if you have a set of charges, let's say if you have one charge in space, let's say Q, and you can determine the potential function of the charge at a distance r, which is a very simple expression, is the inverse function, okay? Unless of a constant, I'm not adding that constant, it's just a relationship between the charge and the distance. The more intense is the charge, the highest is the function. This is usually, there's a constant here. Let's say that in the international system of units, this is measured in volts. Okay? So that's what giving a circuit. The voltage drop, you can determine how much current is going to flow and so forth. But this is the function that's a more generalized concept. So it's important to see how this function behaves in space. R is a distance. If you have a point in space, has coordinates x, y, and z, R would be given by this, right? Square root of this sum of the squares of the coordinates. And then you can plot. We want to use the surface plot to look for this function in the x-y plane. Okay? Because it's a function of two variables in this case. And we can make a representation in which you have a vertical axis. It's the potential value, and the horizontal axis in the plane, okay, you have x and y. I want to know how the function behaves as a function of these coordinates in the plane. So if we have in the geometric space a charge in the, for instance, in the origin, have a charge. This is geometric space, okay? Sorry. X and y. We want to see how the potential changes as we go closer or away to the charge. how intense is the potential. So, I mean, this is geometric space in the plane. I want to see how this function behaves. So if we have that function, in this case, we have the function is going to be simpler. It will be q divided by this part here, x squared plus y squared, root square. If we plot the function, it's going to be something like this, right? Inverse function. Okay? That's what we would see. The inverse function in one dimension would be something like this, but would be in different planes. So these are the locus of points of constant potential. If we cut like this, we have a locus of point of constant potential. Okay? We have to be very careful when we do computing because we have to avoid this denominator to get to 0, right? I mean, if we just try to plot that function in MathCAD, it's going to say singularity. We have to avoid that. So what do? We create an artifact. For instance, if x squared plus y squared root square is smaller than a parameter d, just cut into that value of potential. Okay. So if x squared plus y squared root square equals d, the potential would be given by q divided by d. Okay? So I want to ensure that the potential doesn't grow longer. We go closer to d than d to the charge. So I would say that the potential under this condition would be fixed at this value, held at q over d. Otherwise, you can calculate without problems. Okay? So we would make a computational friendly, let's say, potential. That would be something like this. Q over D if x squared plus y squared is smaller than D. So it would cut like that. Or Q divided by x squared plus y squared root square. Otherwise. So that would be the way to avoid singularity if you want to plot that function. Okay? So if we did that, we would have something like this. A region of constant potential below a very small distance. And if we have larger distance, we're going to have the potential function of that charge. Okay. This is like a mount, right? Mounting, right? With the top. This value here is q over d. It doesn't grow longer. Okay. So that's what looks like the potential function in surface plot format. It looks like those mounts, those mountings. Yes.
Previously, you told that to avoid the singularity, we define d. If it's less than d, then
it's going to cut at that maximum value.
So, how much bigger value will use for d?
You choose it. You play with it in the MathCAD. You choose a value. I mean, for instance, suppose that your domain, okay, is 2 by 2 units. You can choose something much smaller than that. Let's say 0.1, 0.05. It's okay. I mean, observe that. Suppose that you have q equals 1. Let's work with q equals 1 in computing, or minus 1. You don't have to put 2, 3, 4, 5. Just a value, 1. Because you want to see only the features of the function, okay? If you change the relative magnitudes, it's going to be different contributions, it's going to be different. But let's say we make q equals 1. And I would say if your domain the maximum value of the distance to the origin equals to 2, okay? I would use d equals 0.05. If we use that, what's the top value of the potential value? You can calculate. It's going to be the maximum potential. How much is going to be? 1 divided by 0.05 equals 20. Maximum scale you're going to use is going to be 20. So potential is going to be from 0 to 20. If it's minus 1, it's going to be totally negative, from 0 to minus 20. So you're going to have an idea how large is going to be your potential values. Okay? So that's how you do it. So that's computationally, that's how you do the calculation. You avoid singularity by doing some strategy. Okay? Well, since it starts to become a little more complicated if you have more than one charge. Okay? If you have two charges, for instance, Q1 and Q2, then you have a potential grows a lot. I mean, let's say Q1 equals Q2 equals to 1. Okay? Potential grows a lot, very close to each charge. So, I mean, if you want to see so you would have to avoid. I mean, when the position in space gets close to one or the other, so you have to stop and you just cut the potential at that value. Okay? You have to make a strategy to do that. But before we do, I mean, the generalization of this, I mean, let's just take a look qualitatively how it looks like the surface plot of this combination. Okay? So we have two mountains together, right? If we cut like this, it's going to be something like this: two mountains. Right? So we're going to have those situations. The constant potential curves, the logs of constant potential, if you make a contour plot, it's going to be something like this. Like this. So look from the top, make where's the constant potential? So you can take a look. It's going to be, here's the location of the charges, or something like that. I mean, it depends. If you are too close to a charge, it's going to be very circular lines. That's almost as if it was a single charge. And then if you go away, it starts to distort, and eventually this thing starts to mix with the other line. It's going to be something like that. So the lines are going to be isolated, or they want to coalesce, get together, and form a single locus. So you can picture the potential function of a set of charges as the heights relative to ground. Okay? The highest the height, the highest potential. The highest energy is like gravitational energy, and potential energy. The highest position relative to the position to the ground, they have a highest energy. The same thing. Okay?
This happens only in case of identical charges or
Different
different charges?
charges, different signs. For instance, if you have different signs, we would have one to the top, like this, and one to the bottom. We would have something like this. Right? One mountain goes deep downwards. Right? It's difficult to I mean, you're going to see in the map here to see how it looks like. But it's going to be something like that. I mean, those lines go together. So I have a set of mountains, a couple of those up, the others down, downward. Okay. So if you make contour plot of the surface plot, you're going to see the equipotential lines. Equipotential lines are very important, okay, because field lines are orthogonal to potential lines. For instance, for a charge, equipotential lines are circular lines, concentric. Sorry for the bad drawing here. And the field lines are orthogonal to it. Okay? We're going to do simulation for that also in a later workshop. Okay? If I have two charges, let's say plus or minus, it's difficult to see how it's going to be, but the lines are like this, the field lines. And the equipotential are orthogonal to this, so the equipotential are something like this, something like this. I mean, they are orthogonal lines. I mean, we are going to be able to see the equipotential lines in this workshop. Field lines are going to be I mean, the plotting together field lines and equipotential lines is going to be a task for an upcoming workshop. Okay. But let's focus on the charge right now, the potential distribution. If you have now several charges, you have to be careful now. You have to use some vector calculus here. Okay, so if you have n charges, so let's say that Qi is located at the position x, y, y is a vector in 3D space. In 2D space is a vector with two positions only. And let's say that x is the position in space. So I can calculate the potential in x by adding up the individual potentials. Okay? So I have to know the distance between x, y, and x. This distance here, let's call Ri. The potential of this charge, let's say phi I, equals to Qi divided by Ri, and the total potential is an additive of, is an addition of all the potentials. The total potential will be Qi divided by Ri. It's important to express Ri in terms of the vectors involved. So Ri is the modulus, absolute value of the vector difference between vectors, x and xy. Right? So the potential will be given now by this function. Okay? We are going to drop the arrow from now on. We're not going to use arrows anymore here. So we're going to make x, let's call it, to use like mathcal-like variable. So I have an arrow on top like that. Okay? So we assume that we know when to deal with a scalar, with a vector, with a complex number, with a real number. You have to understand when we write the code that this set of variables are vectors, these other set are scalar parameters and so forth. Okay? So the potential would be something like this. And so we have a generalized expression for the potential for a set of any number of charges. Okay? But what do we do regarding the singularities that might happen? How do we implement an algorithm to avoid singularities? So we can make a suggestion in the workshop that I gave to you. We can define a distance, let's call it Ri, such that equals to a parameter d if the distance to the ith charge is smaller than d. Okay? And it's going to be the traditional distance, otherwise. With this definition here, it's easy to avoid singularities. Your potential, if you define in a program block the Ri, your potential is going to be Qi divided by Ri given by this thing here. Okay? So no singularity. So the singularity problem is solved. So you can plot the function without problems. Okay. Now, so this is what we have, for explaining what the potential function is, how it's going to look like, so you can have an idea. So the workshop that I passed to you is aimed to plotting, to do surface plotting, contour plotting, and structured programming. So it's very important to learn how to define functions that receive structured arguments. Okay? So that's the objective. In this workshop, we are going to build a function of 4 arguments. X, capital Q, P, and D. Okay? There's a lot of parameters in these 4 arguments here. Okay? I could reduce all these 3 to a single parameter if I wanted to, but let's make like this so it's easy to understand. Okay? This function, I mean, you have to make a program block to calculate this function. Okay? So what are the parameters? X is the position in XY plane. X is a vector. In math, it's going to be a column matrix. Okay? I'm writing like this so I avoid to make things vertical. I'm just putting like this. But it's a column matrix. Okay? So it's a point in space. So you want to calculate the function at a given point x and y. You're going to plot the function as a function of x and y. The syntax in MathCAD would be something like this: x, x, y. You have to put the arguments here because it's a function of 2 variables equals to x, like this, right? X, y. That's how you write it in MathCAD. I'm writing here in pseudocode. I'm just writing my own way, okay? But you have to write correctly in MathCAD. So that's a point in space. So the 2 arguments pass just with a single letter here, okay? Just put that. What is Q? Q gives the set of charges that you have. If you have n charges, it's going to be something like this. Q is a matrix, column matrix, Q0. Remember, recall that MathCAD starts with position 0. Okay, that's why I'm starting 0. Qn minus 2, Qn minus 1. Transposed. So, column matrix with any charges. So this is an input, okay? That's an input to the potential phi. X, Q. So the program block is going to be, has to be capable of inferring how many charges are in the system by looking at the dimension of Q. So you input the charge to the block will say, what's the dimension of Q? It's this, okay, there are so many charges in the system. Okay? That's the second argument. P is a matrix that has the coordinates of the charges. Okay? Something like this. Is a 2 by n matrix. The xi is a vector, is a column vector, giving the location of the ith charge, xy, yi, transpose. Okay? That's a given parameter. I define my problem. I want 10 charges, 1 minus 1, minus 1, 1, minus 2, minus 3, etc., and make a matrix, define that set. Then I make the location. This is going to be a 2 by n matrix, okay?
So in P, we will also define y.
P defines what?
In P, we will define our x vector, x0, x1, x2, so on. And similarly, we have to define y as well, because x is the function of
What y are you talking about? Which one? You know?
In the X.
Try to speak a little slower because of your accent. I sometimes have difficulty.
X is the function of x and y.
X is a function of 2 variables, yes.
And here in vector
Q and P are not functions, they are given, they are inputs. So we have to write the expression for Q and for P and give this expression to the potential function. Let's say, example, 2 charges, okay? There's an example here. Let's say Q1 equals 1, Q2 equals 1, right? Let's see, Q0 and Q1, right? So like that. Location, X1, X0 equals, this one is exactly like that. Minus 1, 1, X1 equals to 1, minus 1. So who is Q? Q is 1, 1, transpose. Who is P? P equals to minus 1, 1, 1, minus 1. So these are inputs given. So you set up these values, give this to the function phi. Okay?
Inside the P, we define the matrix of
Yeah, these are inputs. So you define, I want to calculate for 2 charges this location. So you define your Q, it's given by this value here, and your P. So you give those constant matrices to the function phi. Okay? Okay? And D is that geometric parameter to avoid singularity. Okay? So we're going to define the distance. So that below this distance, you just cut the potential. Okay. So using this general, so we make this program block. Okay, and then you calculate several scenarios. Okay, you have 2 charges, same sign, different signs. Three charges on an equilateral triangle, let's say, as explained in the text. Okay, there are some guidelines how to place charges, how to place in the plane in a very simple way. Okay, using polar coordinates. This is explained in the class notes in the workshop. And we are going to have a situation with a pentagon. Right? With 2 sets of signs here. I think 3 equal signs, 2 different signs. You see how they have. Then we put all the same sign and one opposite sign in the center of the pentagon. Have 6 charges. Then the last simulation, after you build all this, I mean, you start to get familiarized with acquainted with how it looks like the potential set of charges. Then I want to make a dynamic effect. I want to see, I want to make an animation. I want to see what happens if I continuously change the sign of the center charge in this configuration here. How the lines, the potential lines change continuously, okay? So in the last task that we have to do, you have all the charge. This charge here is a unit charge, but with it's less than unit charge, but it's going to be something like this: sine 2 pi times frame, which is that frame variable in MATCAD, built-in variable, divided by a number m. Okay, you define the m. So when frame varies from 0, which is the initial value, to m, this is going to be varying from 0 to 2 pi. So you have a continuous variation in magnitude and sign between 1 and minus 1. There's one change in sign for one cycle. If you make an animation that goes from 0 to 4m, you have 4 changes in sign. You can see a longer film, okay? You can make m equals 20, for instance, and make an animation frame going from 0 to 80, for instance, and see a film, and save the film, because I want to watch the film, okay? Save the film in AVI format. I'm not sure if Windows is still reading these things, but I have to convert. If Windows doesn't play that, I have to find a way to convert, so MP4 or something like that, so we are able to watch it, okay? Go ahead, slowly.
Sir, we have already used this, I want to know the significance of that 2 pi.
That what? Which one?
Significance of 2 pi.
Just to make sure that when you, because you keep track of it, you know that when frame gets to m, this is 2 pi. So it's a full cycle. Put the 2 pi here, so it's easy for you to understand that when the frame gets to M, you make a full cycle. That's one of the only reasons. Okay?
Then one thing more
And also the other thing, remember, in MathCAD, the arguments of trigonometric functions are in radians, are not degrees, okay? Be careful, don't use degrees, use radians. Okay? The numbers are in radians, okay?